And we are going to open PV watts. First, we have to select the site in New Hampshire. And now, I'm not going to do that again. You should know the DC system size, what it means, the angle, the azimuth. Okay, so we're going to try just an example. We're going to design a DC system size with 6 kilowatts. The angle, let's say 30 degrees, and the azimuth 180. Okay, so this is just an example. You have to use the numbers that you have done in, or you have used in our project, in your project. If we go to the output, here we have this, and this is the yearly or the monthly performance. It's useful because the solar radiation is the amount of sun that we have on the panel itself. Here we have kilowatt hours per square meter per day, and this is the AC energy that we produce in a month, kilowatt hours per month. This is the energy that we produce in January, in February, and this is the annual 7,769 kilowatt hours per year. Okay, great. We have to analyze the yearly demand of our building, and if the yearly demand is close to the yearly production, we are close to the zero energy building. But we can adjust the demand to the production because with this, we depend on the electric company because we will be producing a lot of energy and probably we're not using that energy. So we have to sell this energy to the grid. And if we arrive at home at the evening, then we have to get the energy from the grid. And then usually there is a different price. Okay, so when we are doing this, we can have we have a zero energy building. We produce as much energy as we consume. Perfect. But now, if we are talking about money, the business depends on the electric company and the deal that we have with the electric company. Okay, so we are saving the planet. Yes, we are designing zero energy buildings. But is it worth it for our client? This is not in our, we can't do anything. We can deal with different electric companies, but I don't think there is a difference between different electric companies. At the end, they all have the same business model or the same business plan. So if we want to be really, or if we want to understand what, or we want to adjust the demand and the production, then we need the daily analysis of the production. Here we have the monthly, which is great, and the total yearly production, but we can go further and we can analyze day by day, hour by hour, the energy that we are producing. And it's very simple. So if you scroll down, you see that here we have download results and we can do it monthly or hourly. First, we're going to do monthly. And you see that an Excel file, we can download an Excel file. We click here, we open the Excel file and we have this information. And what is this information? If we extend the elements, okay, the columns. Basically, what we have is the same information as we have in this chart. Okay, the total energy production is 7,700, and here the total yearly production is 7,769 or 68 point something. Okay, so this column is the AC system output, the same column as we have here. The AC, okay? What else do we have in the Excel file? Then we have the solar radiation, kilowatt hour per square meter per day. I think this is the same thing we have here. This is the solar radiation, 3.43 in January, 3.426 in January. Okay, so this column is the same. This is plane of array irradiance. What is this? The irradiance and the solar radiation, those are different things. Solar radiation, as you see, it's energy because it's kilowatt hours per square meter per day, but the irradiance is power. So we have watts per square meter. Okay, so this is different. And then we have the DC array output. Why we need this? The PV panel produces DC, direct current. But unfortunately, 90% of the devices that we're using run on alternate current. Okay, so we have to transform the direct to alternate current. And as you can see, there is a loss. So the DC production is 556 and the AC is 532. Okay, so we lose some energy, a little energy to convert from DC to AC. If we want to maximize the production, we should use devices that run on DC. Okay, there are these kind of devices in the market, but we have to look for them. Okay, so if we really want to save a lot of energy and adjust the production to the demand, working with devices that run on DC, it's slightly better. How much? Well, you see the difference. It's not, we're talking about 30 kilowatt hours per month. What's the price of a kilowatt hour?
In New Hampshire, I think it's like 18, 20 cents somewhere around there.
20 cents, yeah, kind of 15 to 20 cents. But if we have this in mind, 20 cents times 30, how much is it? If we have 30 kilowatts times 0.2, 20 cents, it's $6. We are saving $6 per month. Well, you can have a breakfast or you can, yeah, we are saving $6 per month with the PV array of the DC system. It's 6 kilowatts. It's not a huge PV array. The bigger the building, the more energy we are saving. Probably if we have 10 times as many panels as we had here, we are not saving $6 per month. We are saving 60. And if we have 100 times more, we are saving 600 per month. So if we are talking about the campus, imagine that all these campus is working with, if they have PV arrays on the roof, on all the buildings, there will be thousands of panels. So probably we will be saving thousands of dollars per month. Okay, so in a single family house, yeah, okay, I save $6 a month. It's not a big deal. But if we increase the amount, then we are saving thousands of dollars, and then it might be interesting, okay? And usually devices that run on DC are industrial devices, okay? So computer, I don't think we can find a computer that run on DC, but we can find huge heat pumps to heat up not just a room, but buildings, or probably all the machines that the safety guys are using in this lab. Probably we can find those kind of devices that run on DC. So probably it's worth it. Anyway, it's up to us, and we need to know the difference. Is it a lot of difference? If we're designing a single family house, do we have to lose hours trying to find devices that run on DC? I wouldn't do that. But probably if we increase the scale of the building and the scale of the consumption and the production and the PV array, probably it's worth looking for specific elements that work on DC. Anyway, we need to understand the difference. But with this, well, the good thing of having an Excel file is that we can work with our own graphics, okay? We can select, let's say, month AC system, Imagine that we select all these cells, we insert a recommended chart like this, and we click OK, and we have a graphic with the AC system output in different months. Okay, so here we have the months 1 to 12, and these are the scale in kilowatt hours. So instead of doing what we have done so far, which is copying this chart and pasting it on a PowerPoint, if we do this, it will look nicer. Okay, so if we always create a chart in Excel, it looks nicer than the other thing, and it's we don't look at numbers. We can understand, oh, so in July, we produce the highest amount of electricity. In December is the lowest. Okay, so having this kind of information graphically, it's always better than numbers. Okay, so this is interesting. We can have the same information we have in this chart in an Excel file. That's good. But the hourly file, it's even better. So if you click on hourly, now we download the PV watts hourly, another. Okay. And here we do have a lot of information. It's not just a chart. Here we have every single day of the year and every single hour of each day. So we start on month first. So month 1, it's January, day 1, hour 0 to 23. Okay, so this is one day in January, January the 1st. This is the second day, January the 2nd. Okay. And with this, we have a lot of information because we see when we have a 0, let me. Okay, there is a lot of information here, a lot of useful information. So let's analyze each column. Okay, the last column is the what we want is the AC system production. Okay, and here we have the DC output. Again, there's a slight difference between the DC and AC. This is 1600 and this is 1500 in watts. Okay, but we have more information. We have the cell temperature. So they simulate the temperature of the cell. We know that the optimum temperature of a cell, it's 25 Celsius. That's the optimum temperature. So at this temperature, the PV cell is producing the most energy. So in January, on January the 1st, the temperature of the cell, it's quite good. Here we have 26, 26, 30, 16, 12. Okay, but the average is around 25. So the temperature, the cell temperature, it's quite good in January. It's cold, it will be very cold outside, but it's receiving sun. So that means that if something is exposed to the winter sun, even if it's cold outside, but it's receiving a lot of heat and it's absorbing that heat. So the cell temperature is close to optimum. Okay, what happens in July? If we go to month 7, okay, so here we're in July. What is the cell temperature? We get to 54, 58, 60. Okay, so it doesn't mean that we have 60 Celsius outside. What is the temperature of 60 Celsius? Okay, if there are 60 Celsius, we have 140 Fahrenheit. So it doesn't mean that the air outside is 140, but the cell, the temperature of the cell is 140 Fahrenheit. Imagine a black car in summer under the sun for 10 hours. You touch that car and it burns, okay? So that's the concept of the cell, the PV cell. It's something that it's dark or dark gray, almost black. And if it's exposed to the sun for a lot of hours in summer, then it gets hot and it produces less. Okay, so we can have it's not intuitive, but in terms of PV production, winter conditions are better than summer conditions. Okay, we have more sun, we have more hours of sun, but when it comes to the cell temperature in winter, it's better because the optimum cell temperature is around 25 degrees Celsius. And in summer, the cell temperature can be too hot, so the production can be very, or it's not the optimum production that we have there. We have more solar radiation in summer, we have more hours of solar radiation, but the cell temperature is not optimal. Okay, so we have information about this. Then we have the irradiance, but hour by hour, which is very interesting. Okay, so we don't have just the average, the monthly average. We have the irradiance by hour. We have the wind speed. The wind speed, it's another factor that we use to analyze the PV production. So the standard STC, standard test conditions, it depends on the solar radiation, it depends on the PV cell, and it depends on the wind speed. Okay, so for the wind speed, we have information here about the wind speed too. We have the ambient temperature. Okay, so here we have 2 Celsius. It's not that cold. Okay, so when we have negative Celsius, things are serious. Okay, if we have -5, it's around 23. Okay, so yeah, so in winter, in January, outside we have 23 or even less. Yeah, so there, yeah, -10 or -11. It's 12 Fahrenheit. Yeah, so that makes sense. In Keene, in January, at night, yeah, so here we have at 4 a.m. or 5 a.m. is the coldest moment of the day. It makes sense, okay? So we have the air temperature. We have the irradiance, and this is the beam irradiance and the diffuse. And this is very interesting. We haven't talked about this yet because, well, it would be too advanced. But even in the north facade here, we have light, okay? So we can see that we don't have sun. The sun is not hitting on these glasses, but we do have natural light. We have natural light there, and we do have sun on the south facade. Okay, so that would be the beam irradiance, and that would be the diffuse irradiance. Okay, so we have energy coming from the sun, so we notice it because we see the sun and we see the contrast between lights and shadows. This is what we call the beam, but then we have the diffuse irradiance. And it's not as much as the beam, okay? So here we have values of the maximum, it's 800, and the diffuse irradiance, it's 64. But even on cloudy days, we have some irradiance. So that would be diffuse, it's not beam, okay? A beam irradiance is when we have a perfect clear sky, no clouds, this is the beam. But even if we don't have a perfect sky, blue without any clouds, we do have some solar radiation. The problem is that usually this amount of radiation is not enough to produce electricity on a PV panel. Okay, so we need a certain amount of solar radiation. That's why placing PV panels facing north, it's not worth it. Probably some moments of the day, we will break that threshold and the panel will start producing some energy, but usually it doesn't happen, okay? So that's good, because if we know that threshold, if we know the irradiance at which the PV panel starts producing energy, we can control that, okay? So when does it start producing energy? Especially we don't have the south-oriented panel. If it's oriented to the east, to the west, maybe it's not producing anything in the morning. If it's oriented to the west, but it's producing more in the evening. So we have information. We are not talking about difference between beam irradiance and diffuse irradiance, but at least we have this information. And if we have that specifications in the PV panel, and the threshold, we need an irradiance of 100 to produce something. Okay, so here we have only 2 hours of production. If we place this facing north, is it worth it? No, it's not. Okay, so we have a lot of information, and having information, it's always something good. And the best thing of this is that we can, because looking at this, okay, yeah, so I have all the days here, but can I look at this? Can it generate graphics out of this information? Yes, I can. So let's select all this. This is 1 day. Okay, and I'm selecting all the columns. So I start with hour from 0 to 23. This is 1 day. And here I have all the parameters. If you insert a chart now, what kind of chart? Good question. We're going to select this one with the bars. And we have this bigger. Okay. So I have all the parameters here. When we do this, it's not useful because we are comparing different units. Okay, so we are comparing watts per square meter, Celsius, meter per second, speed, watts. So it's not useful comparing all these elements. I have selected all the columns. I could have selected only 1 or 2 or 3 columns. But if I have everything here, and if you right click on Excel and click on select data, if we want just to compare let's say the DC and AC system output, we can click here and we can make only these 2 columns active. Okay, then I click okay, and I see this, and this is interesting because here I see the difference between the DC and the AC. It's not a huge difference as we told before, but we can say that, or we can understand that this is Monday the 1st. So we start producing energy at 9 a.m. and we stop producing energy at 4 p.m. And something happened here. So there will be like a cloud. Okay, so there will be a couple of hours with clouds, and then the PV production is less than the other one. What if we want to include at different magnitudes? Okay, because here we are comparing 2 columns with the same magnitude. We have watts and watts, and we can compare that. But what if we want to compare the final? Okay, so here I understand the difference between DC and AC, not a big difference. But what if I want to compare, for example, the beam irradiance, which is in different units? This is watt per square meter, and this is watts. So I want to compare the beam irradiance So the solar energy, or the solar irradiance, is not energy, it's the solar power. We have to compare this to the AC production. So let's do this. Then I have to select data. I don't want to show the DC because I'm using only AC devices. And then I want to select beam irradiance. Okay. What's the problem with this? We have two bars, but we are comparing two different units. Okay, so we are comparing watts and watts per square meter. So what is that scale? That scale is the scale of the AC system, because you see that goes from 0 to 4,000. So here we have values. The maximum value, it's 3,000 something. So that scale goes well. But then that scale, the watts per square meter, goes from 400, 800. Okay, so we have this here. But this is watt per square meter, and this is watts. So when we have this in an Excel file, we select this, we right click and format data series, and we can select the secondary axis. But I don't like this. Okay. Maybe I can select this and make it right here. Okay, so with this, I can select or I can compare two things. I can compare the black or the gray one is the AC system output, and the orange one is the irradiance. But the irradiance is connected to this scale here from 0 to 900, okay? And this is connected to that scale here from 0 to 4,000. That's interesting because for sure there's a relationship between the irradiance and the production, okay? So that makes sense. When we have the highest irradiance, we have the highest production. When we have the lowest irradiance, we have the lowest production. But there is some production. You see that when we lower the irradiance, and here it's very low, the production is not that low. Why? Probably this is because the diffuse irradiance, because we are comparing only the beam one. We're not comparing the diffuse irradiance. Okay, so we can here, yeah, we can see how the irradiance affects the production. Probably we should select a different chart, because having the bars here, it's kind of confusing. So when we are comparing two different magnitudes with two different units, I think it's better if we go to chart design, and we change the type, and we combine this. Okay, I like this better. Okay, so here we are combining bars and lines. So the line is the system output, and the bar is the beam irradiance. I think it's clear now. Okay, so this is what happens one day. So we can analyze what happens on January the 1st at 10 a.m. So this is what happens. You can tell me, oh, no, I was here on January the 1st, 2022, and I didn't have this. Actually, I didn't have sun in the morning, and then here we have sun. So it was just different. So we didn't have any sun here. And then at 12, the sun shone for just an hour, and then we had clouds again. This data come from statistics from, I don't know, 50 or 70 years, I don't know. So this is an average of everything that happened on January the 1st, okay? So it doesn't mean that it's a specific day or a specific January the 1st, this is going to happen. So every day, every January the 1st, we're going to have this solar radiation. No, but on average, this is what we will have on that specific day. Okay. So that's it. But yeah, it's one day in January. It would be very interesting to understand what happens the whole month. Can we do that? Yes, we can. But first, we have to understand the where January stops. Okay, so we scroll down, and this is January the 31st. And what is this row? It's 762. Okay. If we go and select the graphic, select data, we are showing two magnitudes, the beam irradiance. Okay, so we select this, edit, and this is the series name. We're not going to change, but we're going to change the series value. So that goes from D19 to D42. But now we want to go to 762. This is the final row. That it's the final day. It's on January the 21st. So we change this 762, and we click OK. And now we select the other magnitude, the AC system output, edit, and we select this, and we have to change this 762. Okay, so here we see the whole month. We see January. And we can see that there are days in which we don't have anything. We don't have irradiance, and we don't have any production. Okay. Why? Because it's cloudy whole day, it's snowing or whatever. So does it happen often? Well, not so often. So when I'm here in January, I have the feeling that it's snowing every day. And it's not. We have a lot of sunny days, more than cloudy days. Okay, so we have those days are perfectly sunny, and this is perfectly cloudy. So this is what we have in January in Kim. It's an average. Maybe we don't have a cloudy day on that specific day. Okay, and it's but on average we have this relationship between sunny days and cloudy days in Kim, New Hampshire. Okay, so that's very useful information, and we can compare the July and January. Let's do that. I'm going to copy this chart here. And I'm going to move down to July. Okay, so this is July the 1st. So I copy the chart here. And now I have to change the number of the rows that I'm selecting. So the first row would be 4363. This is July the 1st. And what is July the 31st? It's 5106. Okay. So if I select the graphic now, the right click, select data, I select this, edit, and this goes from the first row is here. It's 4363. And the last row is 5106. Okay. And okay, it hasn't changed. Why? Oh, because I didn't change it. So the first column is 4363, and the last column is 5106. I click OK, and I have to change the other one. Edit this one. 4363 and 51. Okay, and okay. Okay, so now things have changed. First, okay, so we have fewer cloudy days in July than in January. Makes sense. So I'm going to compare both. I don't know. Oh, I think okay, it's the other way around. Okay, so now we have 2 months. Here we have January, and this is July. Okay, so we can see that in terms of solar irradiance, well, that's interesting. We have if we want to compare this, we would need the same scale. Okay, so that scale goes from 0 to 1200. That goes from 0 to 1000. I'm going to change that scale, and I'm going to type here 1200. Okay. So if we have these two scales, the same scale at both columns, this is 0 to 5000, 0 to 5000, and this is 0 to 1200, 0 to 1200. Okay, so now we can compare. And we have to compare two things. We have to compare the AC output. Okay, let's go in. I'm going to select data, and I'm going to compare only the output. Comments? something. Yes, they are. There's a black line, but there's something weird.
Out a little subtle because most people probably just look at peaks, whereas the width is showing how much more you're getting. Daylight hours.
Okay, so you mean the width of this column?
Yeah.
Compared to the width of that one?
Yeah.
In July, we have 4 hours of sun. Okay, that's a good comment. Probably here, if we analyzed only one day, probably we would see this better. Because in January, we had sun only from 9 a.m. until 4 p.m. Probably in July, we have more hours of sun. Okay, that's the first comment, the width. What about the height of the columns? What is the peak value in January? If we click here, we see that the peak value is 4,600. This is the peak value in January. What's the peak value in July? It could be this one. It's 4,200. Why? We have 4 hours of sun. What? Is what?
Is it not getting too hot to have the efficiency?
The panel is getting too hot and it's losing efficiency. Yes. Okay. So in general, we have more production in July than in January, but it's not that much. At least, I don't know, if you look at this, you say, oh. But if you think about it, previously you say, now in July, we're going to produce much more energy than in January. Well, it doesn't have to be that way because of that reason. This is one of the reasons. The cell temperature. The cell temperature is too hot and it produces less. So the peak production is less in July than in January. Is there another reason to explain that? This is one of the reasons, but there is another one. What did we do here with the PV watts? These are the okay, so I think we did this with 6. And what was the angle? 30. And then we had this production, it was 7. Okay, so yeah, that was it. So the angle is 30. Does it explain the peak production in January or in July? It does. But why? Because the angle, we don't change the angle of the panel, it's 30. Okay, but the angle of the sun changes. So in winter, probably the sun is here, this is winter. And in summer, probably the sun is there. So if the angle in winter is more perpendicular than the angle in summer, that might explain the difference of production. Okay. So if in winter, yeah, we don't know because we don't know exactly the the angle or the right angle that we can have in with 30. Yeah, we should find out the angle of the sun in winter, the angle of the sun in summer, but the angle of the panel makes a difference. So let's do this with two radical options. Okay, so we have a tilt, we have an angle of 30. What would be the optimum? We always tend to say that the optimum is the latitude. Okay, so if the latitude in Keene is 43, probably this angle, the optimum angle would be 43. We have 30. Okay, we're going to do this with two different angles. We're going to do this with 0. 0 means that it's a horizontal, and with 90. 90 would mean that it's a facade. Let's do this and let's try to understand the influence of the angle on the PV production. Okay, so we have 0, the same system size, it's 6 and 0. I don't change anything else. Okay, so I copy this, and now I'm going to, well, the PV production is less than with 30 degrees. With 30 degrees, the PV production, the yearly, it's 7,700. With 30 degrees, with 0 in a horizontal, it's 6,400. Okay, so that makes sense. And now I'm going to download the hourly of this 0. So I'm going to, this is PV watts hourly. Zero degrees. And now I'm going to change this, the same system size, with 90 degrees. And with 90, the production is even less. Okay, so if we are talking about the yearly production, having a facade in Keene is worse than having a flat roof, and having a 30-degree angle, it's better, and probably having a 42, 43 angle, it will be even better. Okay, so the angle matters when it comes to the yearly production. But I'm going to download this, and I'm going to change the, okay, so here the array tilt is 90. And I'm going to do the same. So I'm going to select all the columns up to here. I'm going to insert a graphic. Okay, before doing this, I want to compare the performance in July and in January. So I'm going to select this. I want the title. Okay, so if I select the graphic and select chart design, like here I can add a chart element, and I want title, chart title above. Okay, so this is January. And here I want to add a chart title above, and this is July. But this is July, 30 degrees, and this is January, 30 degrees. And now I copy this. This is January 30. And this is July 30. There you go. Okay. So this is 90. Okay. So I'm going to insert a chart. I'll start with columns. And I'm going to select data, and I just want I want the beam irradiance and the do it again. Okay, if I want to select only the beam irradiance in the system output, I can select all these columns. I can hide them. And now I select the hour and only these two columns until the 23. Now I insert a graphic, a chart, and this. There you go. But now I want this on a secondary axis, and I want to change the chart type, and I want to add this. Okay. So now we have the same chart that we were having before, the beam irradiance and the system output. I want to do this in January. So this, if I select data, I select this, edit. This was up to column 762. Okay, and now the same thing here, column 762. Okay. I have to make sure that this was from 0 to 1200. This is from 0 to 6,000. It was to 5,000 probably because we have values that are slightly higher. Okay, okay, let's do this. So this is in January. Now I want to do the same in July. So I copy this here. This is January 90 degree. And this will be July 90 degree. And now I have to change the data. So the first one, it was from 4363 to 5106. Okay. And now this is from 4363 to 5106. Oh, and I think I have to do the same with the other one, with the AC system output. Oh, no, to write that. Okay. Comments here. If we look at the comments, then we have to look at the scale. That goes from 0 to 6,000, but that goes from 0 to 2,500. Okay, so both scales should be the same. This is 6,000. Okay, that's interesting. What do we see here?
It's 90, the sun in the summer cannot really heat the planet.
Yes, we have a lot of radiation, but the production is very low. Okay, so the worst thing we can do if we want to produce energy in summer is place vertical PV panels. We are wasting a lot of solar energy. Okay, does it make sense? Well, yeah, it doesn't make sense, but you will see a lot of PV panels placed vertically. In summer, this is the worst thing we can do. But in winter, it goes well. Okay, so in winter, what's the peak? The peak in winter is 4,900. Okay, so let's write this down. Uh, 90 degrees. Peak winter. It's 4,956. The units, this is watts. What was the, if we have 30 degrees, what's the peak production in winter? So we have to go to this one. So that was January, 30 degrees. And the peak production, it was 4,601. Okay. And now this is the peak in winter. What is the total yearly? The yearly production, the total, it was 7,768. Okay, with 30 degrees, and with 90, I think it was 5,000. 5,606. Now we have to compare what we have with 0. And I downloaded this one. So I'm going to open this one with 0 degrees. And I'm going to do the same again. What's the total? Do I have the yearly? No, I don't have the yearly energy production. So I have to do it again with 0. Okay, it's 6,465. It's 465. So I'm here with Yeah, the array tilt is 0. So I'm going to do the same. I'm going to hide the columns that I don't want. I'm going to select only the hour up to 23. Insert the chart. Okay. I want to select this as the secondary axis. Change the chart type. Okay. And I want to select now the January. So the final is 762. And with this one, the final is 762. And now I want to do the same with July. This, the chart title is January, 0 degrees. And here I select from 4363 to 5106. And the second one, 4363 5106. Okay, this is July. 0 degrees. Now look at the scale. So that goes from 0 to 1200. And that goes from 0 to 3000. It has to be 45. Okay. So comments now. The peak value in January, in this case, is 2,603. Okay, so if we want to produce a lot of energy in winter, the worst thing we can do is to create a horizontal flat, horizontal PV array. Okay. In terms of yearly production, this is the best one. In terms of peak winter production, this is the best. If we select peak July, we haven't done this yet. Let's do it. The peak production in July probably is this one. It's 4,056. No, this is the 0. And then the 90. This is 90. In July, it's ridiculous. It's 2,106. And with 30, the peak July production is 4224. Okay, so even in July, this is the best. So now we have options. The answer to the question, what's the optimum angle? The latitude, 40, something from 40 to 45. Yeah, we have this automatic answer to that question, 40 to 45. Okay, why? What if I want to use my building only in winter? If I want to use my building only in winter, probably it's a good option, having the facade. If I want to use my building only in summer, well, this is not bad, okay, but probably if I increase the tilt to 45 in summer, it will be worse than this. We will have to check if in summer with 45 degrees is better or worse. If I'm looking at the yearly consumption, yes, something that goes from 30 to 40 something is the best option. But now it's about the integration. Do you want a roof like this? This angle can be 30 to 45. Yeah, this is optimum. But do you want something different? Do you want to integrate this? Do you want to? What do you want to do? Sometimes it might make sense having this, because in winter I'm producing a lot. January. Okay, so maybe it's not a bad option having this. If I could integrate both, I could maximize the production in winter, and I could maximize the production in summer with this angle. So having two different angles with PV panels, maybe it makes sense, okay? Because well, with this angle in January, I'm producing more than here. So it depends on what I'm doing. Anyway, there is not a straightforward. The straightforward answer is 40 degrees. 45, it's good. Yeah, 45. And what about 35? Okay, that's good. So this is what an expert would say. Okay, I can be an expert with this kind of answer. But being an expert means this. Okay, so I analyze the building itself. When are you going to use the building? What do you want to do with the energy? Do you want to sell the energy? Do you want to? Are you connected to the grid? How can I adjust our demand to our consumption? This is being an expert. I mean, it's not just what's the angle? 40. Oh, this guy knows a lot. He doesn't have to think about it. It's just you know, he sees the building and says the right angle, 40, 42. It depends. Okay. But with this, we can prepare a report, and we can do this on a monthly basis. We can have this graphic. I have done this in January or in July, but we can do this in throughout the year, because we have the data, and it doesn't take a lot of time. If you're familiar with Excel, you can have this graphic just by changing the cells, by selecting the data, and select and editing this. And now with this second row here, by changing those numbers, we can have the monthly analysis very quickly. Are we done? Not yet, because we're looking at the production. But what about the demand? What about the consumption? Well, this is something that we can do. or we can easily understand. So I'm now, where am I? Okay, so this is the array tilde 30. Now I'm going to try to adjust my demand with the production. Okay, so there are different issues here. I can try to maximize the production. Perfect. Maximizing the production, I have to test different mounts, different angles. So now I have an idea of what solution is the best. But what if I want to match my demand and my production? Then I need to know the habits of the people, if they are living in a single family house, or I need to use the schedule of the building. And I need to know the devices that this building is using. Well, how can I do this? I'm changing this. I would need another column here, which is consumption. You remember that we did this in F chart. We had this option, okay? So we could include on a monthly basis the consumption of that building, hour by hour. Okay, so I can do that. And if I do this and the units are watts, but now that requires a lot of effort because we need to understand the actual consumption of this building. If we are talking about this, this classroom, if we have 16 computers here or 18 computers, the computers are not working. They are on this saving mode. What's the consumption of computers on a saving mode? 20 watts. 20 watts times 18 times 20 would be 400 watts. Okay, so can we assume that from midnight to 7 or to what time we start? At 9. Okay, so at 9 a.m. now these computers are not consuming 400. A computer, when it's on, it consumes probably 200 watts. 200 watts times 20 computers, this is 4,000. 4,000 plus the electric light. If we have the best electric light, maybe it's 500. Okay, so this can be 4,500. And we have this for a couple of hours. Okay, from 9 to 11. Then at 11, probably the lights will be on and the computers will be on the saving. So we can have 900 for a couple of hours. And then we have another class. So it will be for 4,500 again. And we have 4 hours. And then we have 1 hour with 900. And then we go back to the 400 because nobody is using this anymore. Until 23. Okay, so this is the daily demand. Does the demand depend on, imagine that we have, that this building is running for 365 days. So the demand won't be different. Maybe it will be different in over the weekend, because over the weekend, not all the computers are on, the lights are not on. So there's a different schedule over the weekend. But if we had this, that would be the demand of this building. Okay. Now, how can we match the demand and the production? So I need just these two columns. The AC system output and the consumption. And now if I insert this chart, okay, that's interesting. Here I can see my demand. So even if I'm not using the building, some of these devices are on this standby and they are consuming some energy. Okay, so we have this demand. And here we have the production. So now with this, I can understand how efficient my system is. So that happens on that day in winter. What if I have the same consumption on a day in July? On July. Okay, here we're in July. And okay, so on July the 1st, I paste the consumption, which is the same because it's, yes, if I'm giving exactly the same classes on July, the consumption is the same as in January. Okay, so now if I select these two and I insert another chart like this. Okay, so this chart looks better because, yeah, but can I maximize? Imagine that I'm a manager, I'm the energy manager, the unity manager of this building, and I look at this graphic. And I talk to the property, to Mr. Guinness State College or whatever, and I said, okay, we can improve our performance. What if instead of having this break, just where we have the peak of production, what if we change the schedule and doing exactly the same, working with the same classes, but I have this here and this there. If I do this. Okay, so I'm matching the demand and the consumption. You see? And what if I do something here instead of having this on a standby? What if I have here something like 600 and 600? No, can be have 1,000 and 1,000. No, I can afford. Okay, so what if I give another class here, but it's not 4,000 and 4,000? Well, I am matching the demand and the production. So I'm minimizing the business that we have with the electric company, that having business with the electric company, you always lose. They always win, okay? But if I match the consumption and the production, then the sell or the buy and sell, we can improve this. And of course, why the hell do I need all the computers on during the night? Okay. So this is what an expert does. It's not just 40 degrees. This is not an expert. We have to analyze on a daily basis what we're doing, and we have to match the demand and the consumption. We can do it. Okay, we have the tools. What is the production? We know the production because we have PV watts. We can get this Excel and we can say, okay, what do you want to do on July the 7th? Now, on July the 7th is San Fermin, a very important feast in Spain, and we shut the college. Okay, so that day you are not consuming any energy, and you have to deal with the electric company. No, but on July the 8th, we have a full schedule. Okay, what's your schedule? We start this, then we have a 2-hour break, and then we have to. And what if instead of having the break, you find another activity that needs energy on that specific gap between 11 and 1 p.m. when we have the maximum energy consumption? We can do it. I mean, we have the tools to optimize our production and to match the production and the consumption. So this is what we can continue doing this, or we can do it on a daily basis. At least having this yearly production, it's interesting, and dealing with angles. Okay, so what's the influence of having different angles? Here we can understand that the peak or the total yearly production, but understanding the peak production in winter, the peak production in July, maybe will give us some ideas, because if this building is closed in July, if it's closed in July, probably this doesn't make any sense. And if it's only open in January, I would place the PV panels on the facade, because this is the optimum. Okay? So it's not that. When you know more about this, you realize that it's not as simple as it might seem. If you don't know, it's 40 degrees. Okay, that's it. But if you know more, it's more difficult because you need more data. But once you have all this information, once you have all this data, you can really save energy for your client. And believe me, an energy management on this building and on this campus could save a lot of energy just by controlling the standby of all the devices, just controlling the schedule. And I'm sure that there are a lot of job opportunities to work with this, because what clients know is that they are wasting a lot of money. They know that okay, and probably they can't afford it because the energy price is booming. So this is what the manager should do, but we need data, and we need to analyze this data and then make decisions based on that information.